This video is about semblance-based, structure-oriented smoothing and interpolation. In other words, the SU-SemBase and SU-SemGroup programs, which can be used to reduce noise and/or create traces at new output locations. This is typically done for 2D or 3D CDP stacks or for CDP gathers, but it can be done for other situations.
Semblance is a measurement of the similarity between values. Semblance scanning is a technique which measures the amount of shift between values. Semblance scanning is conceptually similar to cross-correlation to determine the amount of time shift between two traces. However, semblance scanning is used to determine the amount of time shift among groups of traces. And semblance scanning is done over very short time windows. In fact, in SU-SemBase and SU-SemGroup, the time window is one sample. Before getting into more details, I am going to show some test results so you can get some idea of what can be achieved using SU-SemBase or SU-SemGroup. Here is a test 2D CDP stack showing reduced noise. Here, the same test 2D CDP stack shows reduced noise and also creation of missing CDPs. The same test as 2D CDP stack, but now the output is interpolated to half CDP locations. Note that the output CDP key is actually reset to twice the input CDP number, since the CDP key is integer and therefore cannot contain fractions. You can also interpolate to quarter CMPs and so on. This shows part of a 3D stack. The center of the image contains one inline of 3D CDPs. This is after inline noise reduction and creation of missing CDPs. Also note that CDPs are created at the ends of this 3D inline. This is one reason why it is a good idea for your 3D grid definition to be larger than your area of seismic coverage. A close-up of the input. A close-up of the output after inline noise reduction. A close-up of the output after inline noise reduction followed by cross-line noise reduction. Performing cross-line noise reduction requires sorting to cross-line by inline. For this display, I then resorted back to the original inline by cross-line order. This shows some CDP gatherers with the traces within the gatherers sorted by offset distance. The CDP gatherers after noise reduction using offset as the trace locations within the CDP gatherers. Now for some details. I would like to say that SU-SemBase should always be used for stacks and SU-SemGroup should always be used for gathers, but that is not correct. It is better to think about whether you just want to reduce noise or whether you have multiple traces with the same location value. I show some example setups later in this video. Semblance scanning is used to derive the dip at individual sample times using some nearby traces. Those dips are then used to correct the values from nearby traces. This correction is similar to linear move-out correction. The corrected values are then summed and divided by the number of nearby traces. Note that this is not like dip move-out correction. It is not DMO. This is how semblance is defined and computed in SU-SemBase and SU-SemGroup. Generally, semblance scanning is done from scan min to scan max by scan step for every sample in all traces. A short animation of scanning one sample follows. Note that scan min, scan max, and scan step must be specified in units of the location key. Generally, therefore, If the loc key is offset, the scan value should be about 10 or 20 times smaller than if the lock key is CDP. Once the maximum semblance value is found, the associated dip is known. However, the dip value actually undergoes a 3-point interpolation using the semblance values of the neighboring scans. This improves the dip value and also reduces the effects of the scan step granularity. Trace display of the maximum semblance value at each sample. Trace display of the dip values at each sample. Note that random seismic values produce random dip values. I draw your attention back to the semblance computation. Note that this part of the computation is power. Trace display of the power at maximum semblance. When the maximum semblance was chosen, this power value was preserved for use by the dip extend parameter. The dip ext parameter performs a weighted average of the dip values. This increases the time widths of the dips from powerful horizons. Comparison of the dip values for dip ext equals 12 and dip ext equals 48. Slight animation of the increase in time width of dips from powerful horizons when dip ext is increased. Some test data. Output with dip ext equals 0. Output with dip ext equals 12. Now an examination of dip use equals 1 versus dip use equals 0. A test stack. Output using dip use equals 1. This option derives and uses dips at the input locations. Output using dip use equals 0. This option derives and uses dips at the output locations. A side-by-side comparison. To understand why deriving and using dips at input locations is usually better, consider missing CDP22. The most obvious issue is that CDP22 has no input traces near it. But even when the range of traces for semblance scanning is large enough, that means traces with different dips are included in the scanning for output CDP22. The same trace range size for scanning, but now the scanning is done around the input CDPs, not the output CDPs. The derived dips for input CDP20 are more likely to be correct than the derived dips for output CDP22. And the derived dips for input CDP25 are also more likely to be correct than the derived dips for output CDP22. For dip use equals 1, all traces contributing to an output location use their own dip values. At first, it might seem that deriving and using dips at input locations requires more CPU time. But typically this is not true, since there are usually more output locations than input locations. In fact, when interpolating to half CDPs, there are about twice as many output locations. It is true, however, that deriving dips at input locations required more complicated code than would have been required for deriving dips only at output locations. But I believe the extra coding effort was worth it. Now I show a stack test with rapidly changing dip. Note carefully the change on the right side for dip use equals 0. The horizons appear to be squeezed, to use a technical term. It is harder for dip use 0 to follow rapid changes in dip. Keeping dip use equals 0 option anyway, just in case it is better in some situations. Some example setups for simple situations follow, without much comment. Setup of SU Sembase for 2D stacks and all outputs. Setup of SU Sembase for 2D stacks, turning off the scanning and use of dips. An example of interpolating a 2D stack to half CDPs. Changing the scanning range and step size. Setup of SU Sembase for inline 3D stacks showing the use of IGI and IGC 3D index keys. Setup of SU Sembase for crossline 3DP stacks showing sort and use of IGC and IGI 3D index keys. Setup of SUSEM group for CDP gathers using offsets as locations within gathers. Setup of SUSEM group for a 2D CDP stack. Setup of SUSEM group for inline and then crossline for a 3D CDP stack. Setup of SUSEM group to input dips. These dips usually should originate from a previous run of SUSEM group. The big point here is that you can process the traces to produce these dips differently than the traces that you are to. That is, you can use more aggressive filters to produce the dip values and then use them here. Back to a setup of SU Sembase to get nice regular offset intervals within the CDP gathers. Yes, for noise reduction, you should use SU Sem group, but for offset regularization, you should use SU Sembase. The rest of this video contains images of the documentation as of March 2023. I remind you that this can change.